Okay, so last class we began solid geometry by talking about the volume and surface area of these two very basic figures. So just to quickly review before we continue forward, we learned that the volume of a cube is nothing more than the edge to the third power, right? The edge here. And that the surface area of that very same cube will be 6 times, to represent each of the 6 faces, times the edge squared, which is the area of each of those faces. And then we went on to talk about the rectangular prism, which really isn't that different than the cube, aside from the fact that our edge is not universal. We stretch out the edge, we get a length, we have a width, and we have a height that all might be different. The 3 dimensions of a rectangular prism, different than a cube, can all be different. Therefore, we have to represent them with different letters. So it's length times width times height, and that the surface area of that very same rectangular prism will be 2 times our length and width plus 2 times our width times height plus 2 times our length times width, representing all 6 faces, the area of all 6 faces of a rectangular prism, each one which is repeated twice. Well, we're going to move forward today, and I want to just take a quick look at the math reference sheet. You learned a lot of the things on this sheet for Algebra 1. However, in geometry, there is a lot more. This entire last column here have to do with conversions within volume, right? So those are really important for us, especially as we get to application problems, to not forget. And then this whole left side column really is all geometry. And in the world of volume, we have 1, 2, 3, 4, 5 different formulas that are given to us on the math reference sheet, which is universal for all 3 Regents exams. So before we continue today, I just want to take a look at this general prisms formula and explain why it's a little different than the length times width times height that we learned about last class for the rectangular prism. Well, what is this big uppercase B? What does that mean? Well, once upon a time, before the Common Core, it used to actually say that the big B is equal to the area of the, I'm going to use a capital B again, base. So let's see what that might mean. Well, let's look at the lower part of this house over here. Not the top part, but the lower part. The lower part of this house is a rectangular prism. And if we were going to find the volume of the space of that house right there, the bottom part, we would start by figure, well, what's this big B? What's the area of the base? And the part of that house that's touching the ground, the base, has a length here, and over here has a width. There's a rectangle that's touching the ground of this house. That's the base of the house. And this big B, if that represents the area of the base, that means we're going to have to, in this particular case, to find our big B, multiply the length and the width. So in the case of a rectangular prism, the big BH is really the big B, which is length times width, and then times the height. So there's really no difference than big BH or length times width times height, because in that particular case of a rectangular prism, the big B is the length and width. However, that's not universal to all prisms, the length times width. That's only a rectangular prism. And this is a general prism formula for all prisms. A prism is a 3-dimensional shape that has at least one figure that maintains its shape throughout the whole figure. For example, this tent over here, this green tent, the only shape, even though it's made up of 2 triangles and 3 rectangles, the only shape that really maintains itself from front to the back is the front here, which is a triangle. So this is actually called a triangular prism. And therefore, the big B would be the area of the triangle. So the big B in this case is 1/2 lowercase base times height, right? So that right there would be the big B. And then if you wanted the whole find the whole entire volume, if you use the B times H, that's the big B, and then use the H1. Right here, H1 is the base of the triangle. H2 would be the how long that prism extends for, right? And in this first figure right here, yeah, I see there's 1, 2, 3, 4, 5 rectangles and 2 pentagons. However, there's only one figure that maintains itself throughout, and that's the pentagon. So the big B here is the pentagon. So you first would need to find the area of that pentagon and then multiply it by how far back it goes, which we call the H. So you can see the big BH works for all prisms as long as you know how to calculate that big B, which is the area of the base. Well, let's look at these two new figures today. Well, this one right here. Most of you know already that this clearly is a cylinder. And technically speaking, a cylinder could be considered a prism because there is a shape that maintains itself throughout, and that is a circle. So a cylinder really happens to be a circular prism. So you could actually use the big BH if you wanted to. However, we happen to know that that big B has a formula, and that is pi r squared. And how far apart those two bases are is the height. So quite simply, and given to us on the Regents exam, so given to you whenever you take quizzes or exams with me as well, we know the volume of a cylinder is pi r squared, which is the big B, times h. Pi r squared h, right? The volume of a prism is pi r squared h. Now, when we're using a formula, right here, we can see what is the volume of the solid. We can see that the solid is a cylinder, so we have our formula written out. I like to make a little table as usual. Well, here we're looking for the volume, so I'll leave that blank, but the radius is clearly 10 millimeters and the height is 6 millimeters. So I'm just going to substitute those numbers, the radius 10 squared times the height, which is 6. Now, if I were calculating this in terms of pi, I could do it in my head just by multiplying 10 squared times 6, which is 600 pi millimeters cubed, or cubic millimeters. That would be the answer in terms of pi. However, you can see that none of these answers are in terms of pi. So we're going to go to our calculator and we're going to clear it out and put 600 pi. Enter. And you could see that 1884.9, well, you can see that 1884 is the closest answer right here. Well, some of you might have saw that answer and said, hey, shouldn't it be 1885 if they're rounding off? Yeah, you're right. It should be 1885, not 1884. But the reason why is interesting enough that this question is an old question. It's a question that's so old that it was assuming that many people would not have pi in their calculators, which is much more accurate, and that a lot of students would be using 3.14, which is just a general estimate of pi. So you could see if I were to do that right here, instead of using pi in my calculator, if I multiplied it by 3.14, you'll see something interesting that oh, it's exactly 1884, and that's why that answer is that right there. However, the 1884.955592 is much more accurate. All right, so let's continue forward. Oops, I didn't erase that, but I'll erase that then. So here I presented a question. Obviously, we're in video mode, so I'm not going to, you can always pause this to ponder a question. Here's our cylinder. And here's our cone. And we're going to make an assumption here with the cylinder and our cone. The assumption is going to be that the area of these bases, the circle of the cone, the circle of the cylinder, we're going to assume that our B's are equal. And we're also going to assume that this height of the cylinder and that this height of the cone are also equal. Well, is there a relationship that exists between a cylinder and a cone that have exactly the same circles and exactly the same heights? Well, the answer to that question is yes, there is. And the answer to that question is that if we were to have these empty glasses, a glass cylinder and a glass cone, and we turn that cone upside down and we can fill them with water, if we did the experiment, which we often do in class, of how many cones would it take to fill up that cylinder, the answer to that question would be exactly 3. It takes exactly 3 cones that have the same base and the same height to fill up one cylinder. So you could say that that cone is exactly 1/3 the volume of the cylinder, or going in the other direction, you could say that the cylinder is 3 times the volume of the cone. Basically, what we have here is a 3-to-1 ratio, cylinder to the cone, as far as volume goes. So therefore, you could see the relationship between these two formulas. They're almost the same, right? While the volume of the cylinder is just the area of the circle, pi r squared times h, the volume of the cone is 1/3 the pi r squared h. It's exactly 1/3 of the volume of the cylinder. So if we were to take, again, I didn't erase that, that's okay. So if we were to take a cone and a cylinder, and assuming that they have the same base and the same height, find the volume if the radius of the base is 6. So we're assuming that they have the same radius. So the radius of this circle is 6, as is this one, and that they both have the same height. While the height is outside here on the cylinder, the height of a cone is kind of an imaginary line that goes from the very, very tip of the cone to the center of the circle, making a right angle. Well, here, if we were to calculate in terms of pi, the volume of the cylinder is just going to be pi r squared h. And here we have given to us our radius of 6 and our height of 12, right? So therefore, the volume of the cylinder is going to be pi times our radius squared times height, which is going to be 36 times 12, which I believe is going to be 432. So let me double check. 36 times 12 is 432 pi, in terms of pi, and they did give us the units, centimeters cubed. And if we were to do the same exact thing with the cone, we would take 1/3 of pi r squared h. The volume would be 1/3 of pi my radius squared h. The volume would be 1/3 of 432 pi, which would be 144 pi centimeters cubed. 432 pi is exactly 3 times larger than 144 pi. Well, that leaves us with our final shape here, the sphere and then hemispheres. We'll talk about that in a minute. But a sphere, we all know, is a ball. And a ball is a very interesting item and has an interesting formula, right? If we go back to our formula sheet here, we could see it's 4/3 pi r to the third power, right? 4/3 pi r to the third power. It's the only formula on that sheet that has a radius that's cubed rather than squared. Because if you think about the cylinder and the cone, all of those circles are flat, two-dimensional, and then they're extended in some way three-dimensionally through a height. So this is the only case where you have, if you can imagine the point which exists in space in the center of a ball extended to any part of the ball, it goes in every single direction three-dimensionally, which is where this cubed radius comes. But this is a pretty simple formula to use because there's really only your volume and your radius involved. And in this question down here, it says, well, find the volume when the radius is equal to 16. So all we really would need to do here is to substitute one item, which is our radius, which is 16 to the third power. And if you look at our answers, once again, there's no pi. So you could just jump to your calculator here and clear it out and just put that in. 4/3, you can say 4 divided by 3. You can put it in the pi right now if you wanted to. And open up parentheses for your radius, which is 16. And I'm going to power 3 it to the third power and hit enter. And you could see that 17,157 and 17,157 there. Again, they rounded that off, probably using 3.14. So it's as simple as that. But before we finish, I just want to talk about this word, the hemisphere. A hemisphere is three-dimensionally to a sphere what a semicircle is to a circle. It's exactly half of it. So therefore, if we were discussing what's the formula for a hemisphere, some of you could just, go to your calculator and calculate the sphere and then just go, oh, divide by 2. And it is as easy as that, right? And that would be the hemisphere with the same radius. However, the formula is not that difficult to remember because if you just know that a hemisphere is half of a sphere, you can say, oh, it's 1/2 of 4/3 pi r to the third power. And then we can simplify it just by multiplying 1/2 times 4/3, which is 4/6, which is 2/3, which makes sense because 2/3 is half of 4/3. So the formula, the volume for a hemisphere is 2/3 pi r to the third power. This one's not given, and therefore it's up to you how you want to calculate a hemisphere, which is just half of a sphere. Okay, so that's just the quick lesson today. And to sum this up, if we go back to the sheet that we started last class, today we really added a cylinder, just talking about the volume. We added a cone. We talked about a sphere. And then we even added a hemi in the bottom there, a hemisphere. So, quite simply, these formula sheets are good for you to write down. It's good to know them in your head. However, I'm going to allow you to use your sheets for any exam or homework that we have. And we're not going to talk about surface area this year. We're going to just focus for the rest of the year, the few classes that we have on volume. So the volume of our cylinder is pi r squared h. The cone is exactly 1/3 of pi r squared h. Our sphere is 4/3 pi r. And it's the only one that goes to the third power. And the hemisphere is half of that, or 2/3 pi r to the third power. Well, there you have it. I hope you found this useful. Please subscribe to Mr. Frank's YouTube channel. See you next time.